This Zoom session is being brought to you by the Fractal Almond Octaves Z. All right. For today, we will be finishing chapter 8. So today, mathematical induction and 8.6, the binomial theorem. These are pretty subtle, actually. 8.5 is a little unusual in that this is one of the few parts of the book where they emphasize not knowing a result or finding an answer, but finding out how you found out the answer. Mathematical induction. It's a method of mathematical proof. A bit odd. That name is a bit of a misnomer because it's not induction, strictly speaking. Induction, philosophically, is the logic of generalizing from the specific to the reasoning from the specific to the general. You see a black crow, you see another black crow, therefore all crows are black. Well, you know, maybe one day you'll see an albino crow, so it's not necessarily completely accurate. Deduction is reasoning from the general to the specific. Power corrupts, that guy has power, therefore he's corrupt, for example. But the mathematical induction is a way to use a couple of examples of a statement to prove it true in general, provided that you do a couple of things along the way. I actually prefer to call it reasoning by recurrence. It uses an initial case, there's your induction, and an induction step, that's actually a deductive step, to prove the proposition for all counting numbers. So let's start with a proposition, P of n, n's the number, okay, P of a number. So we start from two things, an initial case and an induction step. The initial case says that P of 1 is true. In other words, 1 has property P. Okay, that's the induction case. You just check it out one and see if it works. But then there's what's called an induction step, which is that for any counting number k, if P is true about k, then it's true about k plus 1. So given these two statements, then P of 1, therefore P of 2, therefore P of 3, therefore P of 4, therefore P of 5, and so on forever on down the line. It's sort of like an infinite row of dominoes. Now go over the first one, the first knocks on the second, down the third, down the fourth, and the whole row eventually falls down. Okay, so if P of 1 is true and P of k implies P of k plus 1 for any number k, then it follows that P of n is true for any counting number n. It has a sort of infinity built into there. P of 1, therefore P of 2, therefore P of 3, therefore P of 4, blah, 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 therefore P for all n. So for example, here's a series, 2 plus 4 plus 6 all the way up to 2n. Add all the whole, even numbers from 2 up to 2n, and that equals n times n plus 1. That's the claim. Okay, the initial case, we'll set n equal to 1, and then we have 2, that's one term, equals 1 times 1 plus 1. 2 equals 1 times 2 equals, so yeah, that's true. So the initial case is confirmed. This statement is true for n equal to 1. Now, let's suppose it's true for number k. The sum from 2 up to even numbers from 2 up to 2k equals k times k plus 1. Now let's add the next term. The next term will be 2 times k plus 1. It will therefore be this plus twice k plus 1. K times k plus 1 equals 2 times k plus 1. Pull out a common factor of k plus 1. That'll be times k plus 2. K plus 2 is k plus 1 plus 1. So this thing will equal k plus 1 times k plus 1 plus 1. So this sum equals k times k plus 1 times k plus 1 plus 1. So the induction step is confirmed. The statement true about k implies that it's true about k plus 1. It's true about 1, the initial case. If it's true about k, then it's true about k plus 1. The induction step is confirmed. Therefore, it's true for all n. The sum 2 plus 4 plus etc. up to 2n equals n times n plus 1 for all n. That's induction. Here's a cute one. The sum of the first n cubes equals n squared times n plus 1 squared over 4. Okay. Initial case, easy enough. Set n equal to 1. The left side is 1 cubed. The right side is 1 squared times 1 plus 1 squared over 4. That's 1 equals 4. 1 times 2 squared over 4 is 4 fourths is 1. Yes, so this does work for n equal to 1. Now, let's try the induction step. We will, now remember, this is a little tricky You assume it true for k and prove it true for k plus 1. It's sort of like borrowing in a way. You sort of borrow on the truth of a statement for a value, and your investment yields the same statement true for the next value, and so it grows to infinity. So assume it's true for k. The sum of cubes up to k cubed equals k squared times k plus 1 squared over 4. Now let's add the next term to make the next term in the series. So it'll be this thing, k squared, k plus 1 squared over 4 plus k plus 1 cubed. All right, this is a common factor of k plus 1 squared. Pull it out, k plus 1 squared times k squared over 4 plus k plus 1. Now this we put into a single fraction, k squared plus 4 plus 4 over 4. K squared plus 4k plus 4 is the square of k plus 2. And so you're getting k plus 1 squared times k plus 1 squared over 4. And that equals this. And this is a statement of our theorem for k plus 1. So it's true for k equal to 1. If it's true for equal to k, then it equals for the next value k plus 1. So the formula is proved for all n. Here's an easy one. N is less than 2 to the n for all counting numbers. Initial steps starts with n equal 1. 1 is less than 2 to the 1. That is, 1 is less than true. It's true. So this is true for n equal to 1. Now we'll go through now we'll do the induction step. Assume it's true for k. Let's prove it true. From that, prove that it's true for k plus 1. So we assume that k is less than 2 to the k. Then you add 1. K plus 1 is less than, well, k plus 1 is less than twice k, because, k is bigger than 1 at least, which equals, and since k is less than 2 to the k, twice k is less than 2, twice 2 to the k, which equals 2 to the k plus 1. So k plus 1 is less than 2 to the k plus 1. So assuming it true for k, it means it's true for k plus 1. That confirms the induction step. Therefore, the theorem is proved. And that's reasoning by recurrence. Like I said, it's a little subtle because it's almost cheating, because how the induction step, you assume it's true for a specific value k and prove from that it's true for the next value k. So, all right, let's stop this now.